There are two main ways to transfer energy between systems. Energy is transferred through work and heat. Heat is the natural transfer of energy from a warmer body to a cooler body. Any energy transfer that is not heat is going to be considered work. Initially, some students find the concept of work a bit elusive in the way that the term is used in both chemistry and in physics. Work is described as the product of a force that's applied to an object and the distance the object moves. If the distance and the force are parallel to each other, we identify that work has been done. An object can experience both positive and negative work. For example, if we took a beaker of water and we placed it into a cylinder that's fitted with a movable piston for a lid, some of that internal space would be occupied by both air and water vapor molecules. If the piston isn't moving up or down, then that means that the gas pressure inside of the cylinder equals the atmospheric pressure on the outside. Now, if we reacted the liquid water with solid sodium, the following reaction would occur. According to this balanced chemical equation, when 2 moles of sodium reacts with an excess of water, 367.5 kilojoules of heat is actually given off. In addition to the generated heat, we see that one of the products created is actually hydrogen gas. Inside of the cylinder, the air and water molecules were already occupying the space inside, but during the reaction, hydrogen gas was generated. In order for more gas to occupy that space within the cylinder, well, more space is going to have to be created. So the hydrogen gas pushed the piston upward and created that needed space within the cylinder. The piston continues to move until the pressure inside is again equal to the downward atmospheric pressure. From this reaction, we would say that the system does work on the surroundings, because for the newly formed gas to enter the atmosphere, or in this case enter the volume of the cylinder, it must push back the surrounding air molecules that are actually coming down on the piston covering the cylinder. If we had another scenario where this time more gas molecules were consumed rather than produced, then work would be done on the system by the surroundings. The gas is taking up less space and has been compressed in its volume. Another potential scenario could be that the chemical reaction did not produce any moles of gas. In this situation, we can identify that no work was done by either the system or the surroundings. When a system takes in heat, a portion of the absorbed energy may be used for doing some kind of work. Some everyday examples of work include accelerating a car, charging up a battery, and boiling water, which causes water to go from the liquid phase to the gas phase. The total energy of a system is made up of several different energy types, including the energy resulting from the rearrangements of atoms undergoing the chemical reaction, the energy between the molecules and the individual atoms interacting, and the energy associated with just having a temperature. The stored energy within a system is referred to as the internal energy, and we use the variable U to represent internal energy. When a system absorbs heat and experiences a chemical and/or physical change with the change in temperature, the conditions of the surroundings partially affect those changes. For example, the amount of heat absorbed is exactly equal to the increase in internal energy if no work is done by the system. This would be the case in an ordinary chemical reaction that's carried out in a closed reactor vessel, so that no work is done by either the system or the surroundings. The change in internal energy of a system is represented in many textbooks by delta U, or I have also seen it as delta E. For our purposes, we're going to use delta U to represent the internal energy of a system. Most laboratory chemical reactions are performed in open systems. This just means that some work will be done and there will not be an internal pressure buildup, so the system experiences constant pressure. Again, the work could be done by the system on the surroundings or vice versa. The principle of conservation of energy requires that the amount of heat that is flowing must adjust itself to provide for the work done. So, the amount of heat taken in or released is equal to the change in enthalpy, represented by delta H. Enthalpy is a measurement of the heat within a system under constant pressure. The change in enthalpy equals the internal energy of the system plus the product of pressure and volume. Let's see if we can make sense of heat's relationship to internal energy and enthalpy. If a system at constant volume absorbs heat from the surroundings, the heat equals the change in internal energy, so Q equals delta U. If a system at constant pressure absorbs heat from the surroundings, then the heat equals the change in enthalpy, so Q equals delta H. We have to assume that these relationships represented in the equations is true just as long as they are not in use by work-generating devices like engines or batteries. Any of the terms in these equations can have a positive or a negative sign to communicate what is occurring. For example, if Q is negative, then heat is being lost from the system and the process is exothermic. If Q is positive, that indicates that heat is absorbed by the system and the process is endothermic. If the system is neither exothermic or endothermic, then the system is at equilibrium and Q equals 0.